Welcome to the second part of our lecture series on Möbius transformations in the fourth week of our course, Analysis of a Complex Kind. Remember that we defined Möbius transformations or fractional linear transformations as functions of the form az plus b divided by cz plus d, where a, b, c, d are complex constants such that ad minus bc is non-zero, which just guarantees that f is not constant. These are called Möbius transformations. Here are some facts we showed last class. A Möbius transformation maps the extended complex plane, which is C, together with a point at infinity, to the extended complex plane. We were therefore allowed to plug in infinity for Z, and we get f of infinity is A over C as long as C is non-zero, or f of infinity is equal to infinity if C is equal to 0. We showed that f is a conformal map from C hat to C hat. It preserves angles, it's 1 to 1, and it's onto. If C is equal to 0, then we might just as well assume that D is equal to 1, and then f of C is of the form AZ plus B. These are the conformal maps from C to C. They map infinity to itself, and therefore are conformal maps from C to C. Möbius transformations map circles and lines to circles or lines, meaning every circle is mapped to a circle or a line, and every line is mapped to a circle or a line. Finally, we showed that given three distinct complex numbers z1, z2, and z3, there exists a Möbius transformation that maps z1 to 0, z2 to 1, and z3 to infinity. And we can actually write down this Möbius transformation, and is given by this formula right here. Today we want to construct some actual Möbius transformations. Before we go there, let's prove a few more facts. The first one is that the composition of two Möbius transformations is again a Möbius transformation. And the second one is that the inverse of a Möbius transformation is a Möbius transformation. Let me quickly show you how we would prove this fact. Suppose f and g are Möbius transformations. F of z is az plus b over cz plus d, and g of z is, say, ez plus f over gz plus h. And now suppose we want to look at f of g of z and show that that again is a Möbius transformation, so again has this form. How would you do that? Well, f of g of z means instead of z, we're going to write g of z. So that's a times g of z plus b over c times g of z plus d. And now we plug in ez plus f over gz plus h for g of z. And at the same time, we're going to multiply top and bottom by gz plus h to get rid of the fraction within the fraction. And then left with a times ez plus f plus b times gz plus h divided by c times ez plus f plus d times gz plus h. And now if you multiply through and collect terms, you see it's again off the form something times z plus something. So I'm just going to do this for the top and not for the bottom. So there's again a z term, and it consists of ae plus bg, and a second term that is without any z's, af plus bh. The same thing happens in the denominator, and you see that this is again the form of a Möbius transformation. Similarly, you can find that the inverse of a Möbius transformation is a Möbius transformation. You simply write w as az plus b over cz plus d and solve this for z. And when you solve this for z, you will see that z is a function of w expressed in the form of a Möbius transformation. Now we're able to show the following. Given three distinct points, z1, z2, and z3, and three other distinct points, w1, w2, and w3, there's just a unique Möbius transformation that maps z1 to w1, z2 to w2, and z3 to w3. And it's very easy to see that given the facts we already proved. Here's how you do this. First of all, we know that there's a Möbius transformation f that maps z1 to 0, z2 to 1, and z3 to infinity. Similarly, there's a Möbius transformation f2 that does that for the w's, that maps w1 to 0, w2 to 1, and w3 to infinity. So here's f1 and here's f2. And now all we have to do is look at f2 inverse composed with f1. What's that going to do? f1 maps z1 to 0. f2 inverse maps 0 to w1. And therefore, this composition, f2 inverse composed with f1, maps z1 to w1. Similarly, f1 maps z2 to 1, f2 inverse maps 1 to w2. So the composition f2 inverse composed with f1 maps z2 to w2. Similarly, z3 is mapped to w3. Let's look at an example. Suppose we wanted to find the Möbius transformation that maps 0 to -1, I to 0, and infinity to 1. So in other words, this is our z1, this is our w1, this is z2, this is w2, and this is c3 and w3. I want to show you two different ways of getting there. The first way is to use the proof of the previous fact that we just showed. Therefore, construct the mapping f1 that maps the z's to 0, 1, and infinity, and to construct the map f2 that maps the w's to 0, 1, and infinity. So here's the mapping f1 that maps the z's, therefore 0, I, and infinity, to 0, 1, and infinity. And I just wrote out exactly the mapping that we had constructed before. We have some funny terms in there of the form z minus infinity and I minus infinity. We need to interpret those correctly. Thankfully, they both occur, and they therefore cancel each other out. So the mapping is really z over I. And you can now check the mapping z over I indeed maps 0 to 0. It maps I to 1, because I over I equals 1. And it maps infinity to infinity, because infinity over I is still infinity. f2 is the map that takes the w's, so -1, 0, and 1, and maps those to 0, 1, infinity. And again, we just took the mapping that we constructed earlier and plugged in these values, -1, 0, and 1, and out came the map z plus 1 over -z plus 1. But we need f2 inverse because we need to look at f2 inverse composed with f1. That's going to be our final mapping. To find f2 inverse, we need to set f2 of z equal to w and solve that equation for z. To solve this equation for z, we multiply both sides of the equation by this denominator minus z plus 1 and multiply 3. This gives us w times minus z plus w is equal to z plus 1. And now we collect terms that have a z in them on the right and terms without a z on the left. On the right, we have a z here, and a minus wz over on the other side, which we're going to bring over to the right-hand side, therefore ending up with z times 1 plus w. And on the left, we have w and this 1 that we're going to bring over here, so w minus 1. We can divide by 1 plus w and find that z is w minus 1 over w plus 1. So we now have f2 inverse of w being w minus 1 over w plus 1, and we can therefore look at f2 inverse composed with f1. So here are the two maps again that we construct F1 and F2 inverse, and therefore F2 inverse composed with F1 is the desired map. F2 inverse of F1 of Z can be obtained by plugging F1 of Z in here for W. So we find F1 of Z minus 1 over F1 of Z plus 1. F1 of Z is the map Z over I, we can plug that in. So Z over I minus 1 divided by Z over I plus 1. We multiply top and bottom by I, and end up with Z minus I over Z plus I. That was a rather complicated way of finding this mapping. It was the way that followed our proof. Sometimes a mathematical proof is a very slick proof, but does not give a good constructive way of finding a mapping. There's a much easier way to find this mapping that doesn't follow the proof, but is much easier. So let's look at another approach. We know that the mapping F that we're looking for is of the form AZ plus B over CZ plus D. We want it to map 0 to -1, I to 0, and infinity to 1. Since we want f of I to be 0, we can assume that A is non-zero, because if A was equal to 0, the numerator would be fixed, namely B, and it would be impossible to plug in I and get 0. Therefore, A must be non-zero, and because we can multiply each of these numbers A, B, C, D by a constant without changing the mapping, we can assume that A is equal to 1. Therefore, F is of the form Z plus B over CZ plus D. I just plugged in 1 here for A. Now, f of I is equal to 0, so if I plug in I for Z, I need to get 0. The numerator then becomes I plus B. I plus B must be 0, so B needs to be equal to -I. Therefore, F is of the form Z minus I over CZ plus D. Now let's use the fact that f of infinity is equal to 1. When you plug in infinity here, you get 1 over C. So 1 over C needs to equal to 1, which means C needs to equal 1. And finally, since f of 0 is -1, if you plug in 0, we get minus I over D. That needs to be equal to -1, so D needs to be equal to I. Therefore, f of Z is of the form Z minus I over C plus I, the same function we had found before, but this was much, much easier. Now it turns out there are basically only 3 types of Möbius transformations. Every Möbius transformation is the composition of maps of these types. And the only types there are the maps of the form Z maps to A times Z, which is a combination of rotation and dilation. If you write A as its length times e to the I theta, multiplying by A means rotating by theta and stretching or shrinking by a factor of absolute value of A. The second type is a translation, Z maps to Z plus B, and the third type is an inversion, Z maps to 1 over Z. And those are the 3 types that make up every Möbius transformation. Let's see why that is true. Suppose F is a Möbius transformation. Suppose first that F maps infinity to infinity. We saw that then F is of the type AZ plus B. But AZ plus B is a composition of 2 types of Möbius transformations. First of all, Z gets mapped to A times Z, which is the rotation dilation type, and then we add B to AZ, which is a translation. So AZ plus B is indeed a composition of these 2 Möbius transformations, the rotation and the translation. Next, suppose that f of infinity is not equal to infinity. Then f is truly of the form AZ plus B over CZ plus D, where C is non-zero, and we can divide all the constants by C. Therefore, f is of the form A over CZ plus B over C divided by Z plus D over C. In other words, we can make the constant in front of Z equal to 1, and with that constant being equal to 1, we can simply assume that C is equal to 1. So f of Z is really of the form AZ plus B over Z plus D, with a 1 in front of the Z. But now, let's do a little trick in the numerator. We're going to add an A times D right here, and then subtract an A times D. And we add the A times D by factoring out an A times D plus D. This is the B we had before, and then we subtract AD. But by doing so, we can split out this fraction right here into 2 fractions. The first one is A times Z plus D divided by Z plus D, so that's simply A. And the second one is B minus AD divided by Z plus D. Looking at this carefully, we see again that the Möbius transformation corresponds to a composition. The first part is we're adding D to Z. That's a translation. Next, we're flipping. So we're using an inversion to get the Z plus D into the denominator. Next, we're going to add in this numerator, B minus AD. That's a multiplication by B minus AD, so that's the dilation and rotation kind. And next, finally, we're going to add A to the whole expression, which corresponds to a translation. So again, an arbitrary Möbius transformation is the composition of a translation, an inversion, a dilation, rotation, and another translation. We mentioned earlier the fact that Möbius transformations map circles and lines to circles and lines, but we haven't proved that fact yet. How would you prove this? Well, we can now use this composition result, and we therefore need to only show that these 3 standard types map circles and lines to circles and lines, because every Möbius transformation is a composition of these 3 standard types, and if each of these 3 standard types does what we want it to do, then the composition will do the same thing. Well, clearly, dilations, rotations, and translations preserve circles and lines as circles and lines. In fact, they preserve circles and lines as lines. And so all that's left to show is that the inversion 1 over Z maps circles and lines to circles and lines. We saw the main ideas on how to do that during the last lecture. We looked at a bunch of examples of circles and lines and showed what their images were, and all you'd have to do now is take an arbitrary circle instead of a specific circle and look at its image under the map. Now that we understand Möbius transformations much better, we are ready to study the Riemann mapping theorem. We'll do so in the next lecture.